within our conversions, you spend probably 95% of your conversions in grams to moles, and moles to grams. Right? The other 5% of the time, you're spending dealing with AMUs and atoms or molecules. Right? And again, I ranted about this last week. This whole Avogadro counting atoms or molecules thing is really a lot of nonsense as far as what you would ever really need to use it for. Where you're going to be spending your time is in this conversion factor in here, dealing with your grams to moles, and moles to grams. Right? So you need to be aware of how to shift between those as smoothly as possible. To go from grams to moles, what do you need? You need a molar mass. You need something that relates grams to moles. That information is found on your periodic table. Right? It's the same number as your atomic mass. It's just the units have now become grams per mole. The next one that's tricky is moles of A to moles of B. We are converting between substances. Okay? There's only one way you can convert between substances, and that is in units of moles or molecules if you really went into it. Okay? What we're saying is we are counting one object, and we're looking at that number and relating it to a number of another object. Okay? Well, the only way we know that relationship is through an equation, something that shows us the relationship between those. Okay? I can't just give you a bunch of tires and say, how many cars can you make? Right? You'd have to know how to make a car. And a car has how many four tires? How many tires? 4. Which then means you know you need 4 tires to build that car. You have an equation. You've worked with equations before, these relationships. You just haven't written it out. Chemistry is doing the exact same thing. Every time you see an equation, it's how do you build a car? How do you build the product? It's the same concept. And that concept is going through the numbers of those species. Not their mass, but the number of them. That's where the mole concept helps and why we have to use the mole concept, because if we pick just, say, 4 molecules, that mass is so small we can't measure it. Okay, so the whole point of the mole is to get it up to a measurable value, and then we run our standard reaction as normal. So the only way to convert between species is if you have an equation. What if you don't have an equation? Can't do the conversion. Okay, you don't have enough information to be able to do that conversion. Once you've converted into a different species, you now have access to all the different things that come out of that mole value. And ultimately, again, it comes back to grams. We usually want to go into grams because grams are the unit we can measure. We can't measure moles. We can't even count moles, typically. Okay? We have to measure them, and then we can go back and forth. Okay? There's a variety of different ways to go through and show this. Personally, for me, because I focus really grams, moles, grams, and that's it. Okay? The rest of it is kind of nonsense. If we take a look at what the tutoring center has put together, and I'm not saying the tutoring center put together nonsense, that didn't come out right. They did a good job putting this together. It shows all the possible conversions that can come out of your system. Okay? I personally look at that and think it looks like some weird, violent tank with spears and stabby things. And I think that looks a bit depressing. Okay? I prefer to think about just where I need to exist, grams, moles, grams, and that's the end of it. You'll notice there's all sorts of other little prongy things that come out. Okay? You can get sort of molar mass. Okay? So what they're showing in each of these double-headed sections is how you could convert out to a different unit. Well, converting out to individual molecules, how many times do you count individual molecules? Never do it. Okay, so counting it, while it is a conversion that we can do, it's so rarely done that it's not that big of a deal to stress about. Converting out to the mass of a species. Yeah, that's pretty important. That's how we would measure and make an observation. This one bugs the crap out of me, which is why I told you to ignore it. The volume of a gas. Okay? Yes, there is a relationship between the volume of a gas and the moles of that same gas. That relationship is perfectly valid. Okay? When the moon is directly above you, the seas are roughly level, and the temperature is 43 degrees Celsius. If all of these conditions are met, then absolutely you have superpowers. Why bother to memorize that? Okay? So that relationship is a very dangerous relationship to work because there are certain conditions that must be met. If those conditions are not met, that conversion factor is completely useless and irrelevant, which means why memorize something that has 50 billion exceptions? Okay? It's silly. Don't worry about your volume conversions. Last one is going into molarity. Oh, actually, it's interesting. They looked in going into molarity. We haven't talked about molarity yet. So within this big colorful wheel, your primary focus is the mass one. Molecules, we said, rarely gets used. Gas, I hate. Molarity, we haven't talked about. There's only one thing you have to convert out to. Okay? To do that conversion, we have to know something about mass, the molar mass, and our moles. Okay? So given any question, a very good first step is to convert it into moles. Because as you can tell within these charts, moles is the center. It branches out from moles. So when in doubt, convert to moles and hope for the best. Hope you can find some kind of conversion factor to get you out to something else. So when we went through and looked at that question from, and this is not a quiz now, that question from whatever that exam was, exam 1. There's lots of information given in here. So let's piece together what information we have. For every 1 mole of oxygen consumed, 2 moles of water are produced. What is that referencing?
The balanced equation.
That is actually referencing the balanced equation. I just gave you the numbers for it. Why did I give you the numbers on exam 1? You didn't know it. Okay? You didn't have the context of those. Okay? So what we're saying is that if I take oxygen gas, I can make water. Okay? And in particular, what that thing is saying is that if I have 1 oxygen gas, I can make 2 waters. Okay? Well, your experience on balanced equations, is this equation balanced? No. Okay? So in this new exam, the question changes around a little bit. I didn't realize I made it disappear. And we say we start with oxygen gas and we react it with hydrogen gas to make water. So if we go back to our equation, we'd start with hydrogen plus oxygen goes to water. Is that equation balanced? No. What do we need to do to balance it? Change the coefficients to what? What is the conversion factor between oxygen and water from our balanced equation? Holy crap, that's exactly what I told you in the question. Okay? You have the conversion factor there. It is something coming from the balanced equation. You have to bring that information in. Because when we look at the new format, you have to start applying that information out to the broader sense. So in this case, we're coming up with a balanced equation. Okay? That would allow you to convert between moles of one species and the moles of another species. So if we look at this question, do I have moles of any species? No. What am I given? Grams. So to use the balanced equation, I have to have moles. So what's the first thing I should do to my gram value? Convert it into moles. How do I convert grams to moles? I need the molar mass, which comes from periodic table. You're also given that information. If we look at the original question, you can see there's a pretty big typo on this one. Intentional typo. I told you that the relationship between grams and moles for oxygen was 16 grams equals 1 mole. Okay. Is that technically true? Technically not, because what's our formula for oxygen? O2. Which means when we look at its molar mass, it's 16 for one oxygen plus 16 for the other oxygen, which gets me 32 grams per mole. When I wrote this question, I was fully aware that some people have already seen chemistry and may already be saying that the molar mass for oxygen is 16. They know to look on the periodic table and see that magic 16. So if they start going through and saying, well, I got to double it, okay, or keep it single, I wanted to avoid all that confusion. Because if I said 32 and you looked at the periodic table and said, well, it says 16, he must have made a typo, and you now change it to 16, all hell breaks loose. Okay? So I left it with what the periodic table said because that was an easier conversion to go through and do if you knew some more information. Make sense? Okay. What does this conversion factor now allow me to do? I can now convert my grams of oxygen into moles of oxygen. With the balanced equation that we just looked at, we can now convert our moles of oxygen into moles of water. Okay? I've now converted into a different substance. That's a pretty powerful tool. Okay? If we look at the units that we want for an answer, what unit do we want? Grams of water, not moles of water. So are we done yet? No, you need to again convert moles to grams. Okay? But how do you do that conversion? Molar mass, the exact same way we did the other one, except instead of it being O2 and 32 grams per mole, it needs to be H2O. You'll notice I didn't give you any formulas. Why not any formulas? At that point, you technically didn't know that information. Okay? At this stage, you do. You now have to pull from your nomenclature skills, your balancing reaction skills, using the periodic table skills. There's lots of skills involved in this. And it doesn't end here. Because as we move up in difficulty, we start shuffling in a whole bunch more steps that you'd have to evaluate to go through and answer an overall question. Okay? Questions within this? You guys good or you got one? Okay. So, calculating and using molar mass. I have a feeling you guys have an idea on how to do this, but let's go ahead and test it. Spend a quick second. Sorry, I didn't do that. Copper 2 nitrite. So to start this off, we need a proper formula. Once we know the formula, we can say how many of each of those atoms are present within our structure. We can use our periodic table. The formula for copper is? What is the formula for copper 2? Copper plus 2. Specifies the charge. If we bring one copper together with one nitrite, do we have a proper formula? What do we need? We need 2. Wow, I made the mistake. 2 nitrites to balance. Which then means when we go to figure out our molar mass, we look at the mass of copper, which is 5,5. Nitrogen is stupid sig figs. How many nitrogens are there? There's 2. Remember that 2 applies to everything forwards. So there are 2 nitrogens. Oxygen, 0 grams per mole. How many oxygens are there? There are 4. We have the 2 within and the 2 without. Doubles out, and we'd have 4. Now all you got to do is total it all up, add all those values, and you'd have the molar mass, which didn't actually happen to calculate, but it looked like somebody had 120 something. 155. 155 and change.
155.57.
Okay. Sig figs, should we worry about them? Fine. So if we go through and look, we've got 4 sig figs in our copper, 4 sig figs in our nitrogen, 4 sig figs in our oxygen. When we add those all up, We're going to be doing it based on least what? Unfortunately not. When we're doing addition, it is not the least amount of sig figs, it is the least precise. Where's our precision in each of these measurements? Was it tenths, hundredths place? Which means when we report our answer, we need to report to the hundredths place, which is here, which, oh, look at that. Our answer is 155.57. Right? You may panic because you look at that and you say, well, that's a whole lot more sig figs than we started with. Addition allows for more sig figs. When you add two numbers, you may end up with more sig figs than you started with. Subtraction, you may lose sig figs. The only case where the sig figs stay the same, multiplication and division. Okay? Questions on that? Okay, so a new one. What is the mass in grams of 0.532 moles of copper 2 nitrite? More practice. Now to my least favorite one, because we're converting into atoms, okay, or we're dealing with atoms. What is the mass in grams of 2.55 times 10 to the 23rd atoms? Okay. Believe it or not, you do not need the AMU conversion here, though the AMU conversion would be faster. So I'll keep talking a little bit here. What do we want as an answer? We want grams of lead. What are we given? 2.55 times 10 to the 23rd. Atoms of lead. Okay. So that is our basic work. For those of you in the show your work section, write something. You're telling me you at least know the first two steps of how to solve a question. I can give you points. If you leave it blank, I can't give you any points. So as drawn here, this is a perfectly valid conversion. This will get you through to your answer. You do need to put in the numbers, but you'd have to make sure you find those numbers appropriately. The AMUs of lead to atoms of lead, that conversion factor is found on the periodic table, which I'm just going to abbreviate as PT. Okay? The periodic table gives you the atomic mass unit and also gives you your molar mass, okay, or your grams per mole. So if we wanted to go through and do this, we could very easily pull that, or not easily, but where did it go? Lead, 207. 207.2 AMUs and 1 atom of lead. We're now in AMUs, but I want grams. So you would now need to find the next conversion factor. The conversion factor between grams and AMUs. This is not one you're required to memorize. Okay? So the way this is formatted is now in a way that you are now stuck. Because if you haven't had it memorized, I'm not telling you what it is, you're stuck. Okay? So, is there another pathway? What did I say, 10 to the negative 23rd? Oh, positive 23. Instead of converting our atoms of lead into AMUs, can we convert our atoms of lead into anything else? Moles. So it's interesting. Our very first calculation was to do what? Convert to moles. What did I say you should do as a first step for all these problems? Convert to moles. I wonder why. Right? What is our conversion factor between atoms and moles? 6.022 times 10 to the 23rd. Atoms equals 1 mole. Where does the 1 show up? In front of moles. Good answer. 6.022 times 10 to the 23rd shows up in front of our atoms. What unit am I now in? I'm now in moles of lead. And I want grams of lead. Where do I find that conversion factor? The periodic table. Remember, I said that, what I already forgot the number was. 207.2 grams of lead is 1 mole of lead. And we've now got our problem solved out for us. Okay? I will say that the grams to AMUs, okay, that is one that I do not expect you to memorize, and as such, I will provide that conversion factor on the exam. If it's not already on the exam, I will write it up on the board. It sounded like a few people already went through and memorized that. I think I already forgot it. 10 to the negative 24 grams is 1 AMU. You got to memorize, great, you can do it. If we go through and compare these two features, or these two conversions, they are technically identical. Because what is the relationship between our last conversion in the top one and our first conversion on the bottom? They are inverse of each other. So if one case I'm multiplying, the other case I divide, they equate out to the same thing. Those two conversion factors are identical. The numbers may appear different, but that's only because we've done the inverse calculation on them. Okay? Questions about that? Is it getting any easier? Some yeses, some nos. For the no's, that just means more practice. So I wonder what the next slide is.
What was the answer?
Oh, I have no idea what the answer was. 87.738. Where all the numbers spit out by the calculator. And unfortunately, I just deleted all that work, so I can't even pull it back up. The other thing you're going to have to watch out for is there's lots of powers of 10s showing up in the numerator and the denominator. Anytime you're seeing a power of 10 pop up, you should be putting parentheses with the power of 10 and its scientific number associated with it. So that way you ensure that you are either multiplying those values or that you are ensure that you are dividing by those values. Okay. Same question, we'll go through the, or not same question, same idea. How many fluorine atoms are present in 2.25 grams of fluorine gas? What do we want for an answer? Atoms. You're all shouting out grams. I was like, wait, I thought it was something else. Technically, I'm not going to accept atoms as a correct answer, so try again. Atoms of fluorine. So we could write out fluorine. Is there a shorter way to write out fluorine? Not quite. F2. How do you know it's F2? It's a diatomic molecule. Okay? Fluorine gas is diatomic. The question says fluorine atoms for an answer. So now we've got to be careful. F2 is fluorine gas. What are we being asked to solve for? Fluorine atoms. So it's not F2, it will be F. Okay. What are we given to start with? We're given to start with 2.25 grams of fluorine gas. This case is our F2. Okay. F2 is not the same as F. Okay, so you have to be careful with your conversion factors now. Go through and attempt this question. If you got questions, right? So, there are a variety of ways to solve this question. I happen to pick the way that I think makes the most sense because you are required to know all of this information within this version of the conversion factor. A few people ended up using AMUs. That is a perfectly valid approach to this, but once you're in AMUs, you've got a problem. How do you convert AMUs into grams? You'd have to look that conversion factor up or have it memorized. The people that I saw using AMUs had it memorized, so good for you. Okay? And I guess technically good for me because I sort of have it memorized. Okay? So let's try and do it without that memorization or that value to memorize, because ultimately you are responsible for memorizing Avogadro's number. Okay? So when we start off, we're at grams of F2 and I want atoms of F. Okay? I am converting between substances. F2 is not F. Okay? So that's an interesting dilemma. the way to convert between substances is I would need a balanced equation. Okay? And yes, that may seem a bit odd, but we can do that. How do I convert F2 to F? Is that equation balanced? What do you need to do to balance it? Guess what you now have? Balanced equation, which is now a conversion factor that allows you to convert between those two species. You have an equation. There it is. Okay? The other option is kind of by inspection looking at the formula and saying to make F2, how many fluorines did you need? 2. That's why it says F2. Okay? So we will need some equation to convert between substances. I'm arguing that that is really just our formula at the very end. Okay, so it's just something to be aware of that we'll need as a conversion factor. Because when we go through and do that, we are converting the numbers of these species, not the mass. What am I starting with? Mass. So I should probably convert the mass into a number of fluorine molecules first. The number of fluorine molecules is best represented in what unit? Moles. The very first step is we converted to moles. What did I say you should do as the very first step? There's a reason. Please do it. It helps. So, if we convert, we're trying to get moles of F2. Notice I'm not writing just moles. It's moles of F2. Why? You need your complete unit. If you just write moles, you may very quickly fall into a trap saying it's just F, and that's not the case. I'm trying to get rid of grams of F2. What is the conversion factor between grams and moles? Where's that conversion factor found? The periodic table. Okay. Technically, we have to do a calculation here because the periodic table tells us the molar mass for F, not F2. It tells us for F. How do I get the molar mass for F2 then? Multiply that number by 2. So 19 times 2 gets us 38. Technically, we have 38.00 if we wanted to get fancy on it. Okay. What number shows up in front of moles? 1. Okay. What unit am I now in? Moles of F2. Okay. If we look to my answer, and this is where we could kind of switch these two conversion factors around depending on what you're trying to get to. I look at the answer and I see that I need atoms, not moles. So what I'm going to do is immediately convert into my atom unit, right, which I'll use as quotes here in just a second. I'm wanting, whoops, that needs to be moles. Why should I put moles on the bottom? So it cancels out. It'll be moles of F2. And the unit I'll put on top will be atoms, which I'll put in quotes here, of what? It has to be F2. Why not just F? Avogadro's number has to be the same number of species. I can't convert apples and oranges using Avogadro's number. It has to be the identical species. What is the conversion factor between atoms and moles? Okay, I appreciate the string of numbers there, but you actually didn't give me the unit. 6.022 times 10 to the 23rd atoms of F2. So my 6.022 times 10 to the 23rd needs to show up there. What shows up in front of moles? 1. I'm now in units of atoms of F2. Okay? Are atoms of F2 what I want as an answer? What do I want as an answer? I want atoms of F. How do I convert between those two? This is where I can look at my reaction equation, if you will. And according to my that thing, what numbers should show up in front of F2? What number should show up in front of atoms of F? What do I now have? I have atoms of fluorine as my answer. What did I want for an answer? Atoms of fluorine. Guess what I can now do? Punch it into the calculator and I'm done. Okay? So it is not just a random choice per se of units and conversion factors and just swapping numbers in. Put the unit first. Okay. Always put the unit first. Once you've got the unit, you can then decide where to put the number. The number is going to be based off of the conversion factor that you've been told to memorize. Questions? Yeah, I was going to say that too. Does it feel like it's getting a lot warmer in here? Because it really feels warm to me. Just checking. Questions on that? Okay, are we sure? Because I've had like 2 questions after I've cleared and gone to the next side each time. We're sure we're good on questions. Guaranteed. Now someone's going to ask a question. What is the mass in grams of a single molecule of sulfur dioxide? Being a little bit nice here, I'm telling you that the molar mass of sulfur dioxide, and not only just telling you the molar mass of sulfur dioxide, I even give you the formula, SO2, is 64.07 grams per mole. What do we want for an answer? I disagree. We do not want grams. Thank you. Grams of SO2. What are we given? Yeah, the molar mass allows us to convert between 2 units. I only have 1 unit as an answer. So yes, I have the molar mass. And we could arguably put that conversion factor in here. Okay. I want grams in my numerator. So grams from my molar mass needs to show up on top. And moles needs to show up on the bottom. So I could go through and say 64.07 grams, 1 mole. SO2, right? So cool, I've used that information. But is 64.07 grams per mole equal to grams of SO2? No. So we are definitely missing something. What is that something? What other information are we given? Say that again. We are given in text format the number of molecules of SO2 that we started with. 1 molecule, which we've been saying is quote unquote, is our atoms of SO2. So sure, we know we need to use the 64.07 grams of SO2, and we know the grams need to show up in the numerator because that's where grams shows up in my answer. But we'll notice that if we do that multiplication, do we get just grams of SO2? No. So we have to do a conversion factor. What conversion factor would we ideally be placing in here? I want units, but you're kind of okay there. We want moles of SO2 on top. Why? So it cancels. What unit do I want on the bottom? Okay. Molecules of SO2, or quote unquote atoms of SO2. It is getting really stupidly hot in here. Do we have a conversion factor between moles and molecules? And now you can shout it out again, Josh. We've got Avogadro's number, which was 6.022 times 10 to the 23rd molecules per 1 mole. What happens in my conversion? Molecules of SO2 cancel, and I'm left with grams of SO2. What were you asked to solve for? Grams of SO2. There's your answer. Okay. So it's a question of tracking your units, seeing where the units belong, and just kind of slowly working your way through. Questions about that? We good? I'm going to take that as a yes.
Should the
Frick.
put in the
Go ahead. Yeah.
The answer comes out to be some number value raised to the 10. Negative 22nd.
10 to the negative 22nd. Should we have gotten an incredibly small number for this answer?
Yes.
Yes, we should have. What is the mass of a single molecule going to be? Incredibly tiny. Okay. So we should be getting a very, very small number. So that is actually a good sign. So I can't vouch to say that is exactly the correct answer for that 10 to the negative 22 number. But ballpark, yeah, you're in the right ballpark. The equation concept, how many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? This is one where you would need to look at the equation. If you don't have the equation, you can't answer the question. This goes back to chapter 7. Okay. Not only do we have to have the equation, what else do we need? It must be a balanced equation. So let's look at our equation. Did I balance it? I hope I did. 2, 2, 6, 6. Yeah, it looks like I got it balanced. Good for me. Okay. So now let's answer the question asked. How many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? Okay. Some people can do this by inspection, others cannot. So write it out. What do we want as an answer? We want moles. Actually, no, we want moles of CO2. And we are given, what are we given? Moles of sodium hydrogen carbonate. How many moles of sodium hydrogen carbonate are we given? 1 mole of sodium hydrogen carbonate in our question. Is sodium hydrogen carbonate equal to CO2? No, so I need a conversion factor. What unit should show up in the denominator? That's the bottom. Moles of our sodium hydrogen carbonate. What unit would hopefully show up top? Moles of CO2. Our balanced equation tells us the number of molecules needed to go through and do a reaction. Okay. This is saying moles, not molecules. Okay, so if I had 1 molecule of CO2, how many molecules of sodium hydrogen carbonate could I make? 2. Okay, directly out of it. If I had 2 moles sodium hydrogen carbonate, good question. I changed that around on you. I apologize. 2 moles of carbon dioxide, CO2. How many moles of sodium hydrogen carbonate, 2 molecules of carbon dioxide. 2 molecules, carbon dioxide. How many molecules of sodium hydrogen carbonate could I make? 4. What if I have 6.022 times 10 to the 23rd molecules of CO2? Twice that. Okay, fine, I'll accept that. Okay, our equation tells us the number of molecules. What are moles? The number of molecules. It's just a really big number of molecules. So for all intents and purposes, they are identical, which means I can use the coefficients out of my balanced equation and drop those in front of the moles. What coefficient shows up in front of moles of CO2? 1. What coefficient shows up in front of moles of sodium hydrogen carbonate? 2. I now have an equation. How many moles of CO2 are needed to produce 1 mole of sodium hydrogen carbonate? 0.5. Remember balancing? So there's no way we could have half a molecule. You're right, we can't. This is saying that we have half of a stupidly large number of molecules. Are we allowed to use a half? Yes. Yeah, that is perfectly valid. Okay? So as soon as we move up to moles, we can use fractions of moles anytime we want. Okay? We can't use a fraction of a molecule. Our equation allows us to convert between those substances using moles. Really, really useful. How about the mass in grams? How would I convert that one? Grams, NaHCO3. How many grams are produced if I react 2 moles of CO2? First step is to always
Start with what's given,
convert, well, fair enough.
or put your units. that-
What we want for an answer, what we're starting with. After that, our first conversion is going to be to convert to moles. Are we in moles? Oh, crap. We already started in moles. Guess what our first conversion is going to be? What'd you say there? It's going to be to convert to moles, but moles of our sodium hydrogen carbonate. I need to convert the substance before I can do anything with the grams. How do I convert the substance? Balanced equation. What number shows up in front of sodium hydrogen carbonate? What number shows up in front of CO2? I now have what? I have moles of sodium hydrogen carbonate. What do I want for an answer? What number needs to show up in the bottom? Or what unit? Sorry. Moles of sodium hydrogen carbonate. What unit needs to show up top? Grams of sodium hydrogen carbonate. Where do I find that conversion factor? The periodic table. We'd add up the molecular weights or the molar masses for each of those atoms. We come up with that number. We put that number where?
Next to grams.
Next to grams. Way to not even respond to my phishing. 1 mole underneath. Punched into our calculator. We now have our answer. Same thing as we did the last time around. Okay. The harder part is you now also have to calculate the molar mass each and every single time. Okay. You have the ability. Prove it. Okay? Questions? Okay, we're going to do kind of a blitzkrieg here. I apologize. Oh, actually, I think I put it pretty quickly here. Here's my blitzkrieg. Just want to do one quick concept here, which I thought I'd moved forward. Percent yields. Okay. Let's go through and do an experiment. Let's make aspirin. So we're going to make something. We're going to make aspirin. Nice, simple little drug. Really simple experiment. You guys can do it. Okay. You make 5 grams of it. I make 500 grams of it. Who did it better? You started with roughly 4 grams of starting materials, and let's say you started with roughly 6 grams of starting materials. You ended up with 5. I started with 50,000 grams of starting materials, and I only ended up with 500 grams. I sucked. You did a pretty good job. Okay. Looking at the raw end result number, particularly the mass or moles, does not allow you to compare the validity of an experiment, how good you did. We need to normalize it against something. Have we seen this before? Yeah, it's called your grade. Your grade gets normalized, okay, so that we can assign grades appropriately. Okay? That normalization process ensures that you get a fair grade at the end of the semester. And what we do is we figure out what's the standard supposed to be. We have to have something to compare to. Well, in this case, the extra information you needed to compare to was how much did we start with. Okay? To go through and do a percent yield, it is a really simple calculation. You take how much you actually obtained and you divide it by how much you should have made. How do you figure out how much you should have made? The balanced equation, the mass you started with, the mole conversion, all the way across to how much you could have theoretically have made. Okay? Okay? So that question we just went through and did, where we looked at how much sodium carbonate was produced, okay? That's how you would figure out your theoretical yield. To get your percent yield, you would then take the actual yield, and you divide by the theoretical yield. You multiply by 100. That's it. Okay? And by that's it, you still had to do all those calculations. What we have decided to do for the sake of 130 is that when it comes to percent yield, your calculation will be very simple. Okay, let's see. Do I actually have an example here? Unfortunately, I don't have a simple example. So let's pick a simple example. I need an equation. There's my equation. And this is what we will end with. You start with 5.0 grams of sodium carbonate, 1 gram. Please, nobody actually use the numbers to calculate anything on this. 3.0 grams of CO2. You make, let me figure out some numbers here. Let's just say 2.5 grams of sodium hydrogen carbonate. Based on your calculations, you determine that you should have theoretically made, why not, 2.0 grams. What is your percent yield? Calculate your percent yield. What do you do? What was the actual? 2.5 grams. Divided by the theoretical. Multiply by 100. Now what do we have? You have your percent yield. You've done it. Did we use the 5, the 1, or the 3? No. Why are they there? To mess with your head. Ignore them. If we tell you what the theoretical yield is, that's the theoretical yield. Use that number. Now all you have to do is divide the two. What do we get as an answer here? 125%. Is that physically possible? Yes and no. Okay. No, you should never get a number greater than 100% for a percent yield. Will you get a number greater than 100% for a 100% yield? Yeah, absolutely. Why? Because you screwed up. Okay. That's fine. So if you get a number larger than 100%, that does not mean it's wrong. Check your calculations. Make sure you're using the actual yield and the theoretical yield, but you're good to go.